If you've ever wondered exactly how massive chemical plants and power stations manage to save literally millions of dollars in energy costs every single year, well, I can tell you, it definitely doesn't happen by guessing. It actually comes down to a remarkably elegant engineering concept that pinpoints the exact thermodynamic bottlenecks in any system. Welcome to this explainer on pinch analysis. Today, we're going to unpack the actual mechanics behind heat transfer, and I'll explain exactly how engineers hit that perfect sweet spot between massive upfront costs and daily energy savings.
Okay, let's dive into this explainer. Here's our roadmap. We'll start by defining the pinch point, explore the core cost trade-offs, and then outline the absolute golden rules of pinch analysis. After that, we'll walk through the six-step methodology, look at some really cool real-world applications, and wrap up with why this matters so much for our future.
All right, part one, understanding the pinch point, the ultimate bottleneck.
So, what exactly is a pinch point anyway? Well, conceptually, it's pretty simple. In any heat exchanger, you have a hot fluid transferring its energy over to a cold fluid. The pinch point is just the precise spot in that process where the temperature difference between them is at its absolute minimum. Basically, they are as close in temperature as they will ever get. And unless those fluids are actively boiling or condensing, this pinch usually happens right at one of the physical ends of the equipment. Now, you might be wondering, why does this one specific location matter so much? It's because this is where the entire system design becomes the most constrained. Think of it like a massive, multi-lane highway suddenly merging into a single lane. It completely limits the flow of the entire system. Because the temperature gap is so incredibly tight at this pinch point, the driving force for heat transfer is super weak. That means you need huge heat exchangers just to get the job done there. But by finding this exact point of closest approach and starting our entire system design right there, we can make sure we hit maximum energy targets at the best possible cost. Moving right along to section 2, the cost trade-off, capital versus operations.
This brings us to a really vital term you need to know, the minimum approach temperature, which engineers usually just call delta T min. This represents the absolute smallest temperature gap across which heat transfer will actively occur in your network. And as you might guess from what we just talked about, this almost always happens right at the pinch. Now, technically speaking, any temperature difference greater than 0 allows heat to transfer. But in the real world, relying on a microscopic temperature difference just isn't feasible.
And this creates a massive dilemma for engineers. They're caught between a rock and a hard place. If you choose a very low delta T min, you decrease your need for outside heating and cooling, which sounds great, right? But because that temperature gap is so tiny, you need a massive, highly expensive heat exchanger to actually do the work. That is a huge upfront capital cost. On the flip side, if you allow a high temperature gap, sure, you can buy a small, cheap heat exchanger up front, but you'll be paying a massive ongoing daily utility bill to make up the energy difference. Because of this extreme tug-of-war between upfront equipment costs and daily fuel bills, engineers have to find a sweet spot. For most industrial networks, that perfect Goldilocks zone sits firmly right between 5 and 30 degrees Celsius. Staying in this specific range optimally balances the cost of the raw metal with the cost of the fuel. All right, on to section 3, rules of pinch analysis, the golden guidelines. When you are optimizing a heat recovery network, there are 2 golden rules you absolutely must never break. First, above the pinch, you must use heating utilities only. And second, below the pinch, you must use cooling utilities only. The pinch line essentially divides your entire plant into 2 completely distinct thermodynamic regions. One region is a heat sink that just needs a little extra heat, and the other is a heat source that just needs to be cooled down. To really hammer this home, the pinch actually occurs exactly where the heat transferred between the overarching systems is 0. A cardinal sin in process design is transferring heat across the pinch. If you take heat from above the pinch and send it below, you are literally just wasting energy. You'll end up having to add that exact same amount of heating utility back to the top and add extra cooling utility to the bottom just to compensate for the mistake. Thankfully, we don't have to map out this stuff by hand anymore. Manual methods based entirely on intuition and guesswork, totally obsolete. Today, advanced process simulators calculate these strict boundaries for us perfectly. Which brings us to section 4, methodology in 6 steps, the engineering playbook. So how do engineers actually do this in practice? It boils down to a really precise 6-step playbook. Step 1, you list out all your hot and cold streams, mapping their supply temps, target temps, and heat capacity flow rates. Step 2, you divide the entire plant's temperature range into neat intervals.
Step 3, you calculate the exact heat content for each specific interval. Step 4 is highly visual. You plot hot and cold composite curves, which basically means mapping all of the plant's heating and cooling data onto a single overlapping graph. Step 5, you locate the pinch point, which is exactly where those two plotted lines squeeze the closest together. And finally, step 6, you determine the minimum utility targets and design a beautifully optimized heat recovery network right around that pinch constraint.
Let's look at how this actually applies out there in the field. Section 5, Real-World Applications, Turbines and Columns. Take waste heat recovery in a massive gas turbine. You have extremely hot exhaust gas being used to boil water into steam. In this setup, the pinch point occurs right between the exit of that steam from the water heater or the economizer and the entry of the hot turbine gas. This single physical bottleneck totally dictates the absolute limit of energy you can reclaim. You can't just cross your fingers and wish for more efficiency. The physical pinch strictly dictates the absolute ceiling of what's possible.
Pinch points also entirely govern chemical separation, like what you'd see in a massive distillation column. Now, on an engineer's chart, this pinch is where the operating line, which represents the actual fluid moving inside the column, intersects with the equilibrium curve, which represents the natural boiling points of the chemicals. And what's really fascinating here is that a simple distillation column actually has two of these pinch bottlenecks, one in the top half and one in the bottom. To see how this affects day-to-day operations, just look at what happens when you lower the reflux ratio. That's essentially the amount of liquid you cycle back into the column to help it separate. As you lower this ratio, your system aggressively approaches the pinch point. The individual chemical stages inside the column start doing almost zero actual separation. If you hit the pinch exactly, you would theoretically need a column of infinite height to separate the chemicals. Infinite! Obviously, that's impossible, and trying to get close just wastes massive amounts of energy and capital for absolutely zero gain.
Let's bring it all together. Section 6. Why pinch analysis matters. The big picture. Ultimately, pinch analysis is the key to unlocking the absolute minimum energy consumption possible in heavy industry. By identifying these thermodynamic bottlenecks, facilities can drastically reduce their reliance on expensive outside utilities. Furthermore, it allows engineers to size their equipment at the optimal cost, avoiding the trap of overbuilding massive heat exchangers or underbuilding them and wasting fuel. It improves overall process efficiency from the ground up. But honestly, perhaps most importantly, since industrial processes consume such a massive share of global energy, mastering pinch analysis is fundamental to promoting a genuinely sustainable and energy-efficient future for all of us.
We are simply no longer living in an era where we can afford to guess. Manual methods and gut feelings about plant design are officially obsolete. We have the data, we have the advanced process simulators, and we understand the golden rules of the pinch point. The methodology is incredibly clear. So the only question left to ask is this. Now that we possess the exact blueprint to minimize industrial energy waste, are we fully ready to let the data dictate our designs and build for maximum sustainability?